Okay, so this is a pretty complicated problem from your Gauss's law topic questions. This one's number 7, and it's not too complicated, but when you're not used to analyzing objects in 3D, it can be overwhelming. So when we analyze this, you can see that the x direction is actually coming in and out of the page, and the y direction is going left and right. So what you can tell by the problem itself is that the density of the charges is increasing as we go upward and downward. So here at the center, it would probably have the lowest amount of charges, and then at the surface, at positive and negative z naught, it would have a larger concentration of charges. So this requires us to do calculus. I'm going to start with the Gauss's law equation. So our enclosed integral E dot dA is equal to Q enclosed over epsilon naught. The left side should be pretty easy, but we need to figure out how are the charges distributed, what does the electric field look like, and when we analyze this, if this is a positively charged slab, which they say it's a positive row instead of a negative row, then we know that these positive charges in the center, again, they're not evenly distributed, but they're going to create electric field lines going outward, and it's going to come out on both sides of the slab. Now we want to create a Gaussian surface that has a surface perpendicular to, or that flat surface would be perpendicular to those electric field lines. And so the best surface to do that would be a cylinder. But we would use the pillbox part of the cylinder where the area that we need to analyze is the top and bottom of that cylinder, or the ends of the cylinder. We don't have any electric fields going through the sides, and so our dA is going to be 2 pi r squared. And in this scenario, the r is going to be this radius r here. That stays constant. It isn't an arbitrary r. The electric field is still E, and then the hard part is trying to find that Q enclosed. I am going to solve for the electric field and leave it as a general expression. So we've got Q enclosed over 2 pi r squared epsilon naught. And when we plug in the Q enclosed for the full slab, where we go from positive to negative z, and then for half of the slab, when we go to positive and negative z naught over 2, we can just plug it into this expression without doing any extra work. So I've got my general expression for the electric field. Now I want my general expression for Q total or Q enclosed. So this is from your equation sheet. Usually it's rho with respect to r, but in our expression we know that rho is changing with respect to z, and so we need to analyze the volume with respect to z. The volume we are enclosing is a cylinder, and so the volume of the cylinder is pi r squared L. L is this full length here, but since they give us a direction as positive z naught upward and negative z naught downward, I'm going to call that 2z. And then when we take the derivative, we're taking the derivative with respect to z, not with respect to r. So we can treat all of this as a constant, and we get 2 pi r squared. The derivative of z is just dz. For those of you guys who are in calculus, you can treat it as z to the first power and then use your derivative of a polynomial steps. and that's what we're going to plug into our dV expression. So my general equation is equal to the integral from 0 to some arbitrary z value. I hate that they're using z is the variable and z is the distance, but we're just going to keep it that way. Actually, we'll use z naught for the actual distance. And then I'm going to plug in my row expression, which is c absolute value of z, but we're just going to keep it cz. And then plug in the 2 pi r squared dz for the piece of volume. And you can see that all of the variables are constant except for the z and the dz, so that'll make it an easy expression to integrate. I've got 2 pi r squared times c, integrate z with respect to z, and you end up with 2 pi r c z squared over 2. Again, we're going from 0 to z, reduce that down, and your Q total is equal to pi r, I lost a squared c z squared. Okay, this is my general equation. This is my electric field. When I am trying to analyze the electric field E naught, when when z goes from negative z naught to z naught, then I can plug in z naught into my general expression, and I get E naught is equal to pi r squared c z naught squared over I still have 2 pi r squared and then epsilon naught at the bottom. So I just took my Q enclosed, plugged it in there for z is equal to z naught. Okay, I can reduce a bunch of stuff, and I get c z naught squared over 2 epsilon naught. When I do the next piece, which is when z is equal to z naught over 2, I'm going to use the same expression, except now I've got z naught over 2 here, and that gives me Q enclosed of pi r squared c z naught squared over 4. And then in the denominator, we still have 2 pi r squared epsilon naught times 4. And you can see, again, a lot of things reduce, but you can see that we end up with a quarter of this original expression. C z naught over 2 epsilon naught was my original E naught. And so in the end, our answer would be 1/4 of the total electric field is what we get when we are trying to find the electric field at halfway between the center and the top of our slab. So this is a proportion question. There was some complicated calculus that went into it, but once you understand what they mean by the z direction and the changing density, it's not too bad.